All right, we will continue. We are talking about modal analysis, and we started with the description, mathematical description, because we have a set of differential equation and algebraic equation. So for the modal analysis, what we need to do is to study the behavior of the system around an equilibrium point. And for that, we need to linearize the model. So we have that formulation. But from this formulation, we realize that there is an explicit expression for the algebraic variables in terms of the state variables. So from this equation, as long as this matrix here, the Jacobian of G with respect to Y, if that is invertible, then we can get a solution for Y given by that. If we have that solution for Y, we replace it in the first equation, and then we are able to reduce the system, and we have a model that just relate all the state variables through this system matrix. With that system matrix, we apply what we did in chapter 2, and we calculate eigenvalues and eigenvectors, and then we came up with this expression for the state variables, how they are going to drift away from the equilibrium point, and that's the expression. So from here, we discuss two aspects of this solution. On the right side, we talk about the excitation of the mode. On the left side, by looking at the angle of those terms in the matrix Q, we talk about how these modes are going to appear in the state variable, and we call that mode shape. We also make the definition of damping ratio. So damping ratio will be an index that will tell us how fast oscillation in the system will die out. So we will use it, and I said that if the damping ratio is above 10%, we're happy, we're fine, because the oscillation will die quickly. If you have a contingency, what could be a contingency? An example of a contingency. Equipment outage, generator outage, line outage, transformer outage, those kind of things. Maybe a load outage too, any big change in the system. Then if you have a single contingency that you can tolerate a damping ratio at with a minimum value of 5%. Below that, it's considered that is risky. And if we have those damping ratio, eigenvalues with those damping ratio, we need to take control actions to improve those. So we talk about that. We apply these to the single machine infinite bus system using the classical model. We started here. Why? Because it's simple. We just have two state variables, two differential equation, and nothing else. The system matrix is here, and this is what we obtain in chapter 5, and this is the equilibrium point. So in chapter 5, we calculate the eigenvalues and eigenvectors of around that equilibrium point. And by looking at the imaginary term of the eigenvalue, if we divide that by 2 pi, we get the frequency of this oscillation, which in this case is 1.4. And if you take the inverse of that, you get the period. When we got the simulation, time domain simulation in chapter 6, this is what we obtain when we clear a fault at the terminal of the generator after 0.3 seconds. And as you can see, the period of the oscillation is pretty close to what the model analysis is telling us. In this example, we also discuss the excitation and the mode shape. But this will be more meaningful mode shape when you have multiple machines. In this case, we did it just for completeness. But in the case of when we have the two-machine infinite bus system, mode shape will provide very useful information about the oscillation mode. In this case, that's the eigenvalue. You have this a pair of complex eigenvalue. So you have one here in the second quadrant, and as a mirror with respect to the horizontal axis, you have the second eigenvalue. And because these is the same, we're going to just look at the second quadrant after this example. And here I draw the two lines. One is the the direction in the plane where we are going to have 5% of damping ratio. If you stay along this line, that's what you have. But if you start like moving into this direction, you will find the other line where we're going to have 10% of damping ratio. So if we stay below this second line on the left, below, the system will be good, will be fine, because if you have oscillation, they will die quickly. In this case, we're dangerously close to the line of 5%. So in this system, ideally, we will need to install a controller that can improve this eigenvalue and push it to out of that region, and hopefully on the left side of this line. I think we were here. Example A, what is the difference with the previous example? System is similar, we just have here the two-axis model. With the two-axis model, then we have 4 state variables, 4 differential equations, 2 algebraic variables, and 2 algebraic equations. So in this case, we need to apply the Cron reduction to obtain the system matrix. Yeah. The first thing is, because these are nonlinear functions, we need to linearize the system, and we need to obtain that model. Okay, and that's one I would like to work with you now. So what we're going to do here, I'm going to write down here. Let's pick a few of these. We're not going to do all of them, but as an example, we will get the Jacobian for the first equation and some other equation in the system, maybe an algebraic equation. This is D. There. And then we can pick, let's pick the last one. So that's an equation. And the last equation, algebraic, is going to be this one. Yeah. So to get the Jacobian, let me cancel this. Yeah. So first of all, let's look at the first differential equation. So what are the variables that we need to consider here? So we have the state variables, and you have EQ prime, EV prime, delta, and omega. And the algebraic variables, you have IQ and IV. So which are the variables in this case? You have EQ prime, and you have IV. What about this one? What is this? Is this a variable in our model? It's fixed, so it's a parameter. So this EFD is not considered at this point. It's a fixed quantity that we will calculate at the initialization. So this equation actually just have 2 variables that we need to get the derivative of this back to those variables, nothing else. So what are those terms? So we need to get the derivative of that function. Let's call that function function 1. And we're going to get the derivative with all the variables. So we're going to get the derivative with respect to EQ prime. So you come here to this equation, you get the derivative, and you're going to get -1 over the time constant, 1 over TV0 prime. If you get the derivative with respect to the next state variable, because this function doesn't have that variable, how much is the derivative? It's going to be 0. And the same thing will be for the derivative with respect to delta, the derivative with respect to omega, the derivative with respect to the algebraic variable IQ also is not here. All of these are going to be 0. So the last derivative that is going to be meaningful here is going to be the derivative with respect to IV. Deriving this with respect to IV, because this is linear, is just the negative of this divided by that time constant. negative of xd minus xd prime divided by td0 prime. So we got here the terms for the first row of our Jacobian in the linearization process. And there are just two terms that are relevant. And we will use that to build this Jacobian. For the last equation, that is going to be the derivative of G2. So we have two algebraic equations. So that's the last one. So it's G2 we derive with respect to EQ prime. And as you can see, it's not there. So this derivative will be 0. But then when you get the derivative with respect to ED prime, as you can see it here, that the derivative is just 1. Then all the rest of the variables are going to be this one here are going to be 0. But then when we derive with respect to the current, we need to get the derivative of this again is linear. So you just get this term. It's going to be xd prime plus xl. And I forgot this one, delta. So delta, this derivative is not going to be 0. We need to get the derivative of this with respect to delta. So the derivative of sine is cosine. So the derivative is going to be b2 cosine of delta. So for the last row of the Jacobian, we will have just 3 terms that are different from 0. And we will repeat in the same fashion, for each of the equation we have in the system. Are you with me? Yeah. So let me put the slide again. There it is. Yeah. So we can verify this. Before verifying this, because we have differential equation and algebraic equation, state variables and algebraic variables, we're going to make this partition. When you calculate the eigenvalues of the system, you need to do it to the reduced system. We need to get the system matrix, and for that we need to eliminate the algebraic variables from our representation. So we need to do this partition. So in the Jacobian, which is this matrix, full matrix here, the Jacobian, what you're going to have in this partition is the submatrix that relate the 4 differential equation and 4 state variables. So this matrix is going to be 4 by 4. Then this partition, this submatrix, is going to relate 4 differential equation and 2 algebraic equations. So this is 4 by 2. This one here will relate 2 algebraic equations and 4 state variable. So this matrix is 2 by 4. And finally, this one relate the 2 algebraic equation and 2 algebraic variables. So these is a matrix 2 by 2. And here's the full Jacobian, and here's the partition. Okay. So what we did in the board is actually the first row of this matrix, and we should have the same thing. This is the first term, and everything else is 0 except for the last term, which is what we got on the board. And then we also did, as an example, we did the last row of the Jacobian. So the first term is 0, the second is 1, the third one is the derivative with respect to the angle, which is here, with delta evaluated at the equilibrium point. So this is delta 0. With the speed is 0. The derivative with respect to IQ is this one over there. And I forgot to write it down with respect to ID, which is 0 because this equation do not depend on ID. So we will proceed in the same fashion with the other equation until you get all the Jacobian for the system. When you have the Jacobian, we already discussed what are the dimensions of this. We need to get the partition. So the first 4 rows and 4 columns of the matrix is going to be stored into this matrix. This part into that one, and so on. By applying the Cron reduction, then, we're going to do this calculation. And with this, what we obtain, finally, a reduction in which we will have the direct relationship between the 4 differential equation and the full relationship with the force state variable. So this is the final system matrix. Okay, it's a lot of work, don't you think? Now you need to do the homework, and you need to do it with 2 machines, right? Do you? So we need to do that. That's a lot of work. But hang in there. We're not there yet. With this matrix, then we can use MATLAB. We calculate the eigenvalues and eigenvectors. And here I have the eigenvalues. So lambda 2 is the conjugate of lambda 1. So for lambda 1, you can use the formula we discussed last time to calculate the damping ratio. Look, it's pretty good, 14%. If we're the operator of the system, we will be very happy with this damping ratio. And then we can calculate the frequency of the oscillation, which is 1.28 hertz. What about lambda 3 and lambda 4? How much is the damping ratio? It would be 0, 1. There's no oscillation, right? And we take the real part and we divide it by the magnitude of the eigenvalue. So that's going to be 1. If we express the 1 in percent, it's going to be 100%. So the damping is full. Of course, it's a real eigenvalue, and we don't have any oscillation whatsoever. Another question. We have 2 real eigenvalues. What could be the meaning of these 2 real eigenvalues? We studied in chapter 2 what is the behavior of a real eigenvalue. And because these are negative, this is an exponential decay, right? What can we say? Why do we have 2? Any idea? Not necessarily. First of all, that's an indication that there is no oscillation in that behavior. So you will have just exponential decay. We did that for the RLC circuit. And sometimes we have just real eigenvalue, and the variables converge quickly to the equilibrium point. That's the behavior. But look at lambda 3. What is the value of lambda 3 and the value of lambda 4? How is going to be the exponential decay in each case? A lot faster in lambda 3. Have we talked about this before? Where? In the machine, then we have a mode. What is another word for mode? What is mode, actually?
Oh, it's position on the.
In English. Have you heard that word in another context? Type of reaction, a type of that's a synonym. So this is a type of behavior. And that type of behavior is pretty fast for lambda 4. So what component physically we're describing that's going to be fast? We add IQ damper. We said that's fast. Add damping into the system. What about the other? Well, you have a field winding too. So these 2 real eigenvalues are going to be with the field winding and the IQ damper. Yeah. All right. So if I plot this in the complex plane, then I have these 3 eigenvalues. And also I have the 2 lines, one with a damping ratio of 5% and the other with 10%. The damping ratio for this mode then is going to be 14%, which is pretty good, We should be very happy with this. And the two real, the damping ratio, as Kelly said, is 100%. We don't even bother about those. Those are fine, right? But the ones that are oscillating and are getting close to this segmented line, those can become dangerous. What about if we start like tweaking the system, where we know that a system will not always operate at a given a specific operating point? Would increasing the power in this generator change those things or not? What do you think? Potentially, it will change. If we increase that, why do you think that it can change? What is the argument for that? We always situate ourselves on extreme condition maybe to have an answer. So at this point, 0.5 per unit, we have an oscillation with a good damping ratio. But the question, can that change? When do you think can change? An extreme case, what do we need to happen?
Well, if you have less inertia or more power, there's more power, mechanical power, there's more energy during the disturbance, so it's lead to more acceleration. Same with the lower inertia.
So how many equilibrium point the system has? Very good, David. That's correct. So how many equilibrium point do we have in the system? You're not very sure.
Mathematically, it's signs are a bunch, but yeah, 2.
Yes, yeah. So infinite, but yeah, perfect. Between 0 and 2 pi for the angle, you have two solutions. What is the solution we pick here? The stable focus. But there is another one that is the saddle node, right? What happens when we start increasing the load? These two equilibrium points will start getting closer and closer and closer until one point they merge each other and we have just one solution. Is that a critical operating point? Yeah. What happened in the system? Become unstable, right? So will this have an impact? Of course it will. If we start increasing the solution, as David said, more power will mean that if there is a short circuit at the terminal, the machine will be accelerated even more. And that can make the machine behaving in a different fashion dynamically. And the eigenvalues should change as we move forward. Yeah. So by that description, that's our intuition. What I want you to do, you have a homework, but this is easy. Just change this and play and see whether these eigenvalues that we plot here change in any fashion. Yeah. We said the load. What about if we change the inertia? What about if we change the reactance of that line? Yeah. David in the past asked question about the dampers. Well, what is the impact of the dampers here? Can we play with those parameters and see how the eigenvalues may change? So in that, if we do that exercise, we can get some idea, some feeling of how the dynamic behavior in the system might change. So in this case, because you have just one oscillatory mode, there are two eigenvalues related with, is a pair of complex eigenvalues conjugate. One, we look at the one in the second quadrant, and that will be related with a physical phenomenon in the system. What is the physical phenomenon in that case? We talk about the real ones that are probably related with the field winding and the IQ damper. What is the physical phenomenon in this case? Physical phenomenon. What is happening? What is voltage induced? It's oscillation. It's oscillating. So what that describe? That describe the motion and how the angle will change, right? If we have a disturbance in the system, what will happen with the angle? The angle will oscillate around the equilibrium point. If we're close enough to the stable focus, the angle will oscillate, and that complex eigenvalue will tell you so, right? And what is the description of the oscillation? The frequency of the oscillation, for example, that can be 1. And how do you determine that? Well, you take the imaginary part right here divided by 2 pi, and you get 1.28 hertz. So that is giving a lot of information, and it's telling you in advance, before running anything, that system can oscillate with that frequency, right? And so if we have a disturbance, that can happen. What is the other information we get from here? The damping ratio, we did it already, we talked about it. So it's 14%, and we expect that if this oscillation appear in the machine, they should die very quickly, hopefully. How much quickly? We haven't discussed that part. But I said, if this is more than 10%, operators in the grids will be happy with that, because this oscillation will die quick. Yes.
Yeah, I guess you can go ahead. I guess it deals with.
And this is what we did before. Yes. What is the question?
So I was going to say, so the time plots indicate like the period it corresponds to the oscillation frequency, right?
Yeah.
1.2 hertz. What is the meaning of the natural frequency? And like, can you see the natural frequency on a plot? What is the meaning of the natural frequency?
It's a mathematical definition. If the real part is 0, that will be the natural definition. When you have a second order system, typically they put you the description of the system in a standard form, where you have the damping factors and the natural oscillation, and you got some plot and responses, and you study the overdamp behavior. Do you remember that? Yeah, so all of that is in a standard form, and you use it. But in this case, what we use is actually the frequency of the oscillation itself. If that mode is excited, well, you should see that in the time domain simulation. These are very close. Look, the period is 0.8. But why? Why do you think? One is obtained through linearization, and the other is obtained through full model with all the nonlinear equations. Why one is very close to the other? Because we are very close to the equilibrium point. So if that is the case, then these are going to match. So we're going to use this to anticipate the behavior of the system. But that system is very simple still. So what we're going to do today, we're going to work with this, this system that we study in chapter 6. So we have two machines oscillating. They can we discussed before, they can oscillate together with the infinite bus, or they can oscillate against each other. Those are the two mode of oscillatory behavior in the system. And that's related with the rotation, the motion, right? So that's what we are going to expect here. And then, because we are going to have two oscillatory modes, then the question of Kelly a few classes ago will make more sense. What it was a question? The question was about the excitation. What is the meaning of that number we got for this vector when we were trying to understand what is excitation? So we should see in this example that the excitation for this, the mode will be clear. And if one mode is more excited than the other, we should see that in the time domain simulation. Yeah? So not always we're going to excite all the modes in the system. So most of the time will be a few modes that are going to be highly excited and others are not going to be excited. Yeah, we will do this. I am debating whether, for the sake of time, because we don't have many classes to finish the semester, I'm going to make an exception with this. And before working on this, I'm going to show you an alternative to obtain these metrics, okay? Before giving you the procedure, how we're going to obtain this without the need of deriving all the terms. I want you to tell me what is the meaning of that Jacobian. What does it tell us? Can you think about that? What do you think? You calculated a Jacobian for a different application before. You did it for the power flow problem using Newton-Raphson. But what is the meaning of a Jacobian matrix? What is telling you? What do you think?
All the variables are related with each other. The coupling of all the variables.
The coupling? In which sense? In mathematical terms, it is in a linear sense, right? Kind of a sensitivity, right? So if for some reason you move out of all the variables, you move just in one variable, we have how many, in this example, we have 4 state variables, 2 algebraic variables. If I am at the equilibrium point, let's think about the Jacobian. If we're in an equilibrium point, and let's pick the first variable, EQ prime. We're at the equilibrium point, and delta x and delta EQ prime is 0 because we're at the equilibrium point. What about if I move EQ prime a tiny bit? What do you think will happen? Huh?
The other variables won't change.
If I move this a tiny bit, what do you think will happen? Oh, this is EQ prime. And this is going to give you what? All of this. Delta F1. So if I don't move it, I have a sensitivity. This is 0. We're exactly at the equilibrium point. Function is 0, right? But if I move it a little bit, the function will change. Now we're not at the equilibrium point. But what the sensitivity will tell you is a linear approximation of the change. So it tells you, if you change this a small quantity with this sensitivity, you can anticipate how much the function should change due to that specific change in the variable. If we do that for this variable, then we will have the same situation for the other equation, delta F2, and all the way to the last one, which is G2. With that little change that we apply in that variable, through this sensitivity, we can anticipate how much should be the change that we have in those equations. Are you following me? Yeah. But what about if we do this backward? Because we're engineers, we're trying to find something that can be complex, getting all this with analytical expression. We want to try to do it in an easy way, thinking about the problem. What about if I have the function? We have all the function in our code. If I put for EQ and all the other variables, I put them right at the equilibrium point, what we're going to get? For the function, all the functions. All of them 0, right? F1 all the way to F4, G1, and G2, because those are algebraic, all of them are going to be 0. So we are there. And now we're going to move the EQ prime a tiny bit, and I will do it in the computer. We have the function. Instead of sending the equilibrium point, I will put the equilibrium point plus a little magnitude for EQ prime. So if I do that, I will observe how much is the change. So I will call the function, I will tweak this variable a little bit, call the function, observe how much are the changes. If I observe how much is the change, then we're going to do the following. And in that fashion, I will know exactly what is the first term of that Jacobian. Is that easy? So that's sensitivity. Okay, how much we're going to move this? 0, 1? Any number? So this is like the definition of the derivative. So if we make that change very small, that will be very close to the derivative. So we are going to use a very small number. So for this, we can use an epsilon. What is epsilon? Any small number that we want to pick, yeah, and we will use it. And from this second equation, then we will observe how much is in the change in that function divided by the change that we apply in the variable, and we will, by calculating that ratio, we will approximate what is the term in the second row, first column of the Jacobian. And in that fashion, all the way to the last term, oops, delta G2, delta EQ prime, delta G2, the derivative with respect to EQ prime. So we will do this. Apply a change in the variable, observe the change, calculate the ratio, and approximate the derivative. When we are done with that first step, what we will have? The first column of the Jacobian. How are we going to do it for the second column? Same procedure, but instead of changing a little bit the first variable, we will do it with the second one. We apply a change, call the function, see how much change, get the ratio, and we get the approximation. Are you with me? Yeah. Let me go back to the code here. So that's the Jacobian that we calculated before. And that's the system. And those are the equations. So we have these equations already. And that's the system. This is the system that we program this code for that system. Probably I need to increase the font. Where do I do that? Here. Font. I don't know how much. 18 maybe. There. Yeah. So that's the code that we had before. And let me see. That's the code. With that clearing time, then we got the solution for the system. So that's the system we're dealing with. Now, I don't need to run the time domain simulation for this. All that I need is the equilibrium point. So in our code, first of all, we calculate the power flow. And with the power flow, we calculate all the state variables in that machine to finally calculate the initial condition. I will stop the code right there. Okay? We can integrate this into the code later, but for the sake of time, we will just stop the code right there. So if I invoke the code now, the code is halt at this line. Yeah, now I can come here to the command window and do my calculation, right? What is the function that we created for this system? It's right here. That's for the short circuit. And that is the function for when the short circuit is clear, right? So we have an equilibrium point calculated already, which is x0. That's the equilibrium point. So if I call this function f time, what time are we going to use? for this application, it doesn't matter because the function is independent of time, right? So I will put 0, and then the vector that I'm going to put as an input is the equilibrium point. How much we're going to get? 0, because it's the equilibrium point, and that's exactly what we get. This is 10 to the minus 15, right? So this is what we're going to do. We're going to, let's do it manually first. We're going to define epsilon. It needs to be a small quantity. Let's use 10 to the negative 4 for now. And we will apply the principle that I described here in the board. So how much is delta F actually? Delta F is just the function F evaluated at the perturbed point now, right? Because the function at the equilibrium point is going to be 0. So this delta F is going to be just F at the perturbed point. So in this case, F is going to be what? It's going to be the function that we used before, this one. But we need to perturb the first variable. So I'm going to define here xp, p for perturbation, is going to be x. Let me define something else. Delta x is going to be, how many variables do we have? 6 there, all of them 0. Yeah, but in the first term of that vector, now we're going to have x0 at the first term plus the epsilon, right? So that's the new xq prime. New x, what I am doing here? That's delta x. So this is the other thing. This is delta eq prime. So if I am just changing this, all the variables, all the rest of the variables remain the same. Then this is nothing else than epsilon, right? Because we're going to define that. So eq prime is going to be eq prime 0 plus epsilon. So delta eq prime is going to be this term minus eq 0 prime, which is epsilon. So this term is going to be directly epsilon. So I don't need that delta x actually. What I need is trying to, no, that's right. For the first term here, because all of the other are 0, this is going to be epsilon. So that's the change we will apply to what? To the xp, the perturbed point, which is going to be x0 plus delta x. Delta x. So if I do that, you can see the term here, x0 and xp, and they look pretty much the same, but only eq prime has been changed a little bit. Okay, yeah, now we're good to go. Now what I can do, I can calculate this delta function. How did we call the function before? We have f and g together. I think we call it h. I think so. I'm going to call it delta h. It's going to be nothing else than the function times 0 evaluated at the new perturbed equilibrium point, and that's what we get. Yeah. So if I pick this number now we have this. We have this. Now I need to divide it by this change that we apply to the variable. But that change is epsilon. So all that I have to do is to take this delta f, the one that is in MATLAB, divided by epsilon, delta x, we divide this by epsilon, and that should give us the first column of the Jacobian. Are you with me? Are you following? Yeah. Let's do this in a code, because we need to do this for the 6th variable, and we have to create here a for loop from 1 to 6, and we need to repeat the step that we just did. So we're going to create the delta x as we did it before. This is going to be, each time that we go into the loop, we're going to just get a vector of zeros. But then at iteration k, we will be dealing with the k variable. So we will just modify, we're going to modify just that variable, and we're going to add epsilon. Now xp, which is the perturbed point, is going to be x0 plus delta x. So that's the new point. Then we will use delta function. Is going to be there. It's going to be the function that we have for the system evaluated at the perturbed point there. And now we're going to get the Jacobian. This is not the full Jacobian. This is going to be the k column of the Jacobian. And that is going to be nothing else than delta h divided by epsilon. Right there. So if we put end, we will close the loop, and we should have the Jacobian matrix. Is that the result we should get? We don't know yet. Why? Because this is the full Jacobian. You have all the differential equation and algebraic equation together. So we need to do the partition. So I'm going to call J1 the first submatrix that we have. So that's for the first 4 rows and 4 columns. This is 4 by 4 matrix. That's the first one. Then we have J2, 4 rows, and the last 2 columns. The third matrix, last 2 rows, and the first 4 columns. And the last submatrix is going to be the last 2 rows and the last 2 columns. So now we need to calculate the system matrix, and as we discussed already, this is J1 minus J2 multiplied by the inverse of J4 multiplied by J3. And that's supposed to be the system matrix. Okay. The last equation we use is that one. So one was done using analytical expression, and another is done using a numerical procedure. And as you can see, in this case, we obtain about the same. So what I'm going to ask you for the homework, that you proceed with this numerical implementation. If you do it correctly, you should be able to get the correct eigenvalues and eigenvector for the system. Yes?
So when you do you have to use I guess the diagonal term? Because like in F1, there's also like IQ or whatever it was.
Right. You use the same value that you had before. So you start from the equilibrium point. All the variables are at the equilibrium point. And then you change just one variable at a time. And no, because we are trying to build the Jacobian matrix So we are going to start one variable at a time. If you pick the first variable, as I explained here, you obtain with this procedure the first column of the Jacobian. But then you will go to the second variable, ED prime. Then what you're going to do, you are going to pick x0 and increase by an epsilon just the second variable, ED prime. With that new value, you will calculate how much the function will deviate divided by the epsilon, and you will get the second column of the Jacobian. And you will repeat in that fashion until the very last variable, and you will get this large Jacobian matrix. By doing the partition, we separate what are algebraic equations from differential equation and algebraic variables from a state variable. You partition the system, and then you apply the Cron reduction to obtain the system matrix. Okay, as you can see, we get the same result. Let me move this here. This second column is about the same. This one, yeah. It's just rounding numbers, right? So if we round this to 3 decimals, we should get the same result. Okay.
And so delta F is just the value of the function at the equilibrium point plus epsilon for one variable.
Yes.
Minus the equilibrium point at the result for F, right? That's delta F. The function evaluated at the equilibrium point.
Yeah, but the function evaluated at the equilibrium point is 0. Yeah. So when I put there delta F, F1, for example, is going to be F1 at the perturbed value minus F1 at the x0, but this one is 0, right? Yeah. So in that fashion, we can calculate this. Now, when we come back to this system, we don't have to suffer with the analytical calculation of all the equations. How many equations we had in this case? Do you remember? 18. 8 state variable and 10 algebraic variable. So that's a lot of calculation, 18 by 18. That would require a lot of calculation. But if we proceed in this fashion, you should be able to obtain the Jacobian, the system matrix. How big is going to be the system matrix in this system? 8 by 8. Calculate the eigenvalues there. Get the plot as we did it here, and try to anticipate what are the modes. How do you say, David, the mode or type? The type of dynamic behavior. That doesn't mean that those are going to show up when you excite, you perturb the system, but they potentially may appear in the variable. Okay? Yes, I can do that. I can do that. Okay. Any other question before we close for today? Yeah. You're welcome. Oh, yeah. Okay. Thank you, guys. See you on Monday.